Our project was to drop a chicken and then in turn calculate the force of acceleration of gravity downward on the chicken, and then also the impulse force upward of the flap of the chicken's wings, accelerating it upward.
In these 3 screenshots and throughout the fall, the chicken exerts 3 impulses on the air, accelerating it upward.
We know that the mass of the chicken is 2.7 kilograms, and from there, through the energy lens, know that the initial potential energy of the chicken, if it did not flap its wings as it fell, will be equal to the final kinetic energy of the chicken.
We know that the potential energy equation is mgh, and the kinetic energy equation is 1/2 mv squared. Setting the two equations equal to each other and factoring in the 1.1 meter fall that was calculated, we can find that the final velocity is 4.7 meters per second. The next step is to find the average velocity. We can do this by subtracting the final velocity from the initial velocity of 0 meters per second and dividing it by 2 to get 2.35 meters per second. Finally, we can solve for t. T is the amount of time it takes for the chicken to fall completely to the ground from the person's hands. T can be found by taking delta y, or the distance to the ground, and dividing it by v average, or the average velocity of the chicken falling to the ground. Using those two numbers, we can find that the t equals 0.47 seconds. If gravity were the only force acting on the chicken on its fall, then all of the work we've done so far would be completely correct. However, the flap of the wings of the chicken gives the chicken an impulse upwards. The sum of those forces will be the final acceleration.
Here, we took the velocity final, which is equal to 2.93 meters per second. We got this number from the data on Logger Pro from our video, and then we plug this number into the velocity over time function to discover the average velocity, which is 2.93 meters per second, divided by the time it took for the chicken to fall, which was 0.53 seconds, and we get the average acceleration to be 5.53 meters per second squared. We now switch to the dynamics lens and establish a free body diagram as seen on the left. We add the forces acting on the chicken, the first of which being the force of gravity, and the second being the impulse force of the chicken's flaps. We set the positive and negative direction, and the positive being downward with the force of gravity, and the negative direction being upward with the force of the chicken's wings. We then plug that into the sum of the forces equals mg diagram on the right. We establish that the force of gravity minus the force of the chicken is equal to ma. And then after plugging in all of our numbers, we come to the conclusion that the force of the chicken is negative 12.1 newtons.
Continuing to look at this problem through a force lens, one can see that the constant force of gravity is 27 newtons, and the force of gravity plus the force of the impulses provided by the chicken is 23 newtons. So those are the two possible sums of forces that we have here. The sum of force will always be 27 newtons unless there's an impulse, and that's the spikes we can see that were created by the impulses just for a short amount of time. The 4 Newton difference was found by taking the 12.1 newtons we found and dividing it by 3 impulses to get 4 newtons. 27 minus 4 is 3 newtons. Next, we move on to the acceleration versus time graph, which may look familiar because forces cause acceleration. The acceleration due to the chicken is 1.5 meters per second in the negative direction, and once again, we can see the acceleration spikes due to the impulses of the chicken.
Because the acceleration of the chicken downward was only 8.5 meters per second, this goes to show that the falling chicken fell slower due to the fact that its force upward prevented it from falling at the speed of a normal falling object.